In this video, we will discuss colligative properties. Colligative properties are properties of solutions that change depending on how many solute particles you have dissolved. So what that means is that it doesn't really matter what the solute is, it just matters about the number of solute particles which relate to the Van't Hoff factor. So let's talk about a couple of them and then we'll do some math. So one of them is that when you dissolve things in water, you may notice that their boiling point or freezing point change, and we'll do the math behind that. But one reason that the boiling point changes is that the vapor pressure lowers. So when we did gases, we talked about how the vapor pressure is just the pressure of a substance typically above its liquid phase or solid phase, but most likely it's liquid phase. And so if I have pure water here, water has all of these water particles above the surface of water that cause humidity, and that is called its vapor pressure. But if I add some salt or some ions here, so I chose positive ions, but if I add some positive ions here, then what that means is that there are fewer solvent particles at the surface, aka there's fewer water particles at the surface, which means of course there's going to be less particles that are going to be able to enter the gas state, and so the vapor pressure is going to be less because there's going to be less humidity because less water can go into the gas phase. Okay, freezing point depression, what that means is that you can lower freezing points by dissolving salt or an ionic compound. Typically, it can be a non-ionic compound like sugar, but it's typically by dissolving salt, some sort of ionic compound, in your solution. So we see this all the time, is that when there's a snowstorm, typically the roads are iced or icy because it gets cold, and with the snow and rain mixture that the roads can get icy. And so what we typically do is we treat the roads with salt, and what that does is instead of water's freezing point maybe being 0 degrees Celsius, it may lower it to negative 20 degrees Celsius, and so the roads won't be as slick. Okay, and that's actually very effective. And what that has to do is with this formula, which is on your formula sheet, and what this is the change in freezing point. Okay, that's what this is. Okay, not the freezing point. Notice this will be the change. So typically, like if it's water, we might solve for this to be 8. Okay, that doesn't mean now the new freezing point is 8. That means that the freezing point has been lowered by 8, because freezing points can only ever be lowered. That's why it's called freezing point depression. And so that equals this I, which is the Van't Hoff factor. Kf is a freezing point constant. That's 1.86 degrees Celsius times kilograms divided by moles. That is on your formula sheet. And then an italicized M, that is molality, which is moles of solute divided by kilograms of solvent. Okay, so let's look at another one, and that is boiling point elevation. And so typically when people make pasta, if they've made pasta before, one thing is that takes a while for the pasta to get in its al dente state. So what a lot of people do is they boil water. But water, if you're in Indiana or at 1 atmosphere about of pressure, water's boiling point is 100 degrees Celsius. And so it would be nice if when we're cooking that we could speed up how fast pasta could cook to get to its al dente state. So what typically happens is people will add a pinch of salt to their boiling water or to their pasta. And the reason why is that what that does is that elevates the boiling point. Okay, so what that means is that water can get to maybe 110 degrees Celsius without boiling, which means that your pasta can cook a little bit faster. Okay, and so it's got a similar formula. It's got delta TB, which is the change in boiling point. So if I solve for 7 degrees Celsius, what that means is that the boiling point has been elevated by 7 degrees Celsius. It is the Van't Hoff factor times the boiling point constant, which is Kb, and if it's water, that's going to be 0.512 degrees Celsius kilograms divided by moles, and then times the molality. Okay, so let's do some example problems. A lot of these are just plug and chug, but they're a little bit weird at first until you've just done a couple. Okay, so what this says is we want to calculate the boiling point elevation, which means we're not calculating the boiling point, we're just calculating the boiling point elevation, or how much it gets raised. If we had 2.1 moles of sugar or glucose, which is a non-electrolyte because it's a hydrocarbon, and it's added to 2 liters of water. Well, one thing that's good to know is that 1 liter of water equals 1 kilogram of water. So this is really 2 kilograms of water. And we are trying to find the boiling point elevation, so that is this formula up here, and I'm just going to copy and paste it. Okay, so we have a non-electrolyte. That means our Van't Hoff factor is 1. We are dissolving this in water. I know it doesn't say that. That is my bad, but I wrote the problem, so I know that it is. In Kb, if I look at my formula sheet, that is 0.512 degrees Celsius times kilograms divided by moles. And then we're going to multiply this by the molality. Okay, so molality, italicized M, equals moles of solute divided by kilograms of solvent. So we have 2.1 moles of solute, which is glucose, and we're dividing it by the kilograms of solvent. Water is our solvent. That is 2 kilograms. And so I get a number, but what I can also do is just plug in 2.1 moles divided by 2 kilograms. And that equals the change in boiling point. So my change in boiling point when I do this is 1 times 0.512 times 2.1 divided by 2. I get 0.5376, and the unit would be degrees Celsius. Let me just prove it to you. Moles is in the numerator here, but it's in the denominator there. Kilograms is in the numerator there, and in the denominator over there. So we are left with just degrees Celsius because the Van't Hoff factor does not have a unit. And so that's how much my boiling point changes. What if the question says, what is the boiling point? Well, water's normal boiling point is 100 degrees Celsius, so we would add 0.5376 degrees Celsius, and that would give me 100.5376 degrees Celsius as the new boiling point. Okay, let's look at B. B says calculate the freezing point when 34.5 grams of aluminum chloride is added to 300 milliliters of water. So 300 milliliters of water, that is 0.3 liters, which is 0.3 kilograms. That formula for us is up here, so I'm going to just copy and paste it since we're dealing with freezing point. Okay, so what I have is I'm solving for freezing point, not the change in freezing point, but the freezing point. So not this number, but I'll need to get that first. The Van't Hoff factor for aluminum chloride is, I've got 1 aluminum, 3 chlorines, so that would be 4. The Kf for water, I'm just going to look up here, that is 1.86 degrees Celsius times kilograms divided by moles. And then I just need to get the molality. Well, like I said up here, molality is equal to moles of solute divided by kilograms of solvent. I know that I've got 0.3 kilograms of solvent. I just need to get the moles. So I'm going to take 34.5 grams of aluminum chloride. The molar mass of aluminum chloride is 133.33 grams of aluminum chloride for every 1 mole of aluminum chloride. And so when I do that, I get 0.259 moles of aluminum chloride. And what I can do is I'm just going to move this actually there. Let me make this a little bit smaller. Or just move it out of the way. And so what I can do is solve for this. Delta TF equals 4 times 1.86 times 0.259 divided by 0.3. And I get 6.4232 degrees Celsius. A lot of people are going to leave that as their final answer, but this is asking for the freezing point. Freezing point can only ever be depressed or lowered, and so what I would say is that water's normal freezing point is 0 degrees Celsius. So subtracting away 6.4232 degrees Celsius, that's going to give me negative 6.4232 degrees Celsius as the actual freezing point of water here.